We've come to the third and final video on special relativity. Because what we want to consider now is an object acted on by a force. The force is equal to mass times acceleration. But the force also can be thought of as the rate of change of momentum, and momentum is mass times velocity. Now, what that means for this object here is if it's acted on by a force, a little bit later, it will be moving with some additional velocity. Now, suppose I thought of this as seen by somebody here who sees this whole thing as moving with some velocity u. Now, what does this person see? We've seen in the second video that the velocity seen by this observer is not simply v prime plus u, but something somewhat more complicated. But the particular characteristic of it was that if v prime and u are both less than the speed of light, then this person, looking at this object with this additional velocity, will see it as traveling at a speed less than that of light. But you see, there's a problem here. If this is the momentum, and if the force continues to increase the momentum, it continues to increase the velocity, then according to this, as it gains momentum, it must be going faster and faster. And with this expression, there is no limit as to how fast it could travel. Clearly, this must be modified. The corrected expression for the momentum is given by this. P is the mass times velocity divided by the square root. The thing to notice is that if the velocity is much less than the speed of light, this is very small, and what we would have for b much less than c is that p is approximately mv, exactly what we had before. But as the velocity becomes closer and closer to the speed of light, this becomes closer and closer to zero, and thus the momentum becomes very large. So if we made a graph of this, it would look like this: momentum here, velocity there. Here you get the usual behavior of the momentum being the mass times velocity, but as the velocity comes close to the speed of light, the momentum grows. You see, now one can talk about the force being the rate of change of momentum. The momentum becomes larger and larger and larger, but the speed never exceeds the speed of light. I would like to do a little bit of playing around with our newfound expression for the momentum. Here I've squared it. M squared b squared divided by 1 minus b squared over c squared. Now in this, it's the mass. It doesn't depend upon velocity. And I'd like to put it by itself on the right-hand side. And after a little bit of algebra, I end up with this. Well, this is certainly the momentum squared times c squared. But what is this? I'm going to call it a squared. In other words, a itself would be mc squared divided by the square root of 1 minus b squared over c squared. I'm interested in figuring out what this quantity A represents physically. And I'm going to do it by finding out what it's equal to if the velocity is much less than the speed of light. Again, with a bit of algebra, one can show that A is approximately equal to c squared plus 1/2 mv squared. But this last term I recognize, that's kinetic energy. That means that this entire thing, the sum of these, must correspond to an energy, total energy. So I'll write E is mc squared divided by the square root of 1 minus b squared over c squared. So this is the total energy of an object traveling at the velocity v. It's interesting to note, though, if the object is at rest, p is equal to 0, you get a equals mc squared. One of the better known expressions in the 20th century. I hope you've enjoyed this brief introduction to special relativity, and maybe it'll motivate you to go on and look at other features of physics. Thank you.